Alright, in this video we're going to be looking at an introduction to sequences. Most likely you saw sequences in pre-calculus as one of the topics covered in pre-calculus. A sequence a sub n is a function from the natural numbers, and sometimes it will also include 0 to the complex numbers. Typically for us it's going to be just the real numbers. And we're going to do a couple examples of finding the first 5 terms of a couple of different sequences. So the first one is going to be a sub n is equal to negative 1 to the n. A sub 1 is going to be negative 1 to the first power, which is negative 1. A sub 2 is going to be a negative 1 squared, which is going to be positive 1. A sub 3 is going to be negative 1 to the third power, which is negative 1. A sub 4 is going to be negative 1 to the fourth power, which will be positive 1 again. And a sub 5 will be negative 1 to the fifth power, which is equal to negative 1. So the terms of our sequence, the first 5 terms, negative 1, 1, negative 1, 1, and negative 1. And that pattern will continue. And notice that we alternate between a negative 1 and positive 1. And it doesn't have to be just 1 and negative 1. It could just be a positive and negative. And we'd call this an alternating sequence. Okay. All right. Second one we're going to look at is a sub n is equal to the sine of n pi over 2. So a sub 1 is going to be the sine of pi over 2, which is 1. A sub 2 is going to be the sine of 2 pi over 2, which is the sine of pi, which is 0. A sub 3 is going to be the sine of 3 pi over 2, which is minus 1. A sub 4 is going to be the sine of 4 pi over 2, which is the sine of 2 pi, which is 0. And a sub 5 is going to be the sine of 5 pi over 2, which is at 1 again. And so this has another pattern. It's a cyclical pattern based off of the sign on the poles on the unit circle here. So this pattern would go 1, 0, minus 1, 0, and then continue 1, 0, minus 1, 0. Okay. All right, let's take a look at one more. Let's look at a sub n is equal to 2 over 2n plus 1 pi. So a sub 1 would be 2 over 2 times 1 plus 1 pi, or 2 over 3 pi. A sub 2 would be 2n plus 2 times 2 plus 1 pi in the denominator, so 2 over 5 pi. A sub 3 would be 2 times 3 plus 1 pi, and that'd be 2 over 7 pi. A sub 4 would be 2 over 2 times 4 plus 1 pi, or 2 over 9 pi. And a sub 5 would be 2 over 2 times 5 plus 1. And that is going to be 2 over 11 pi. So that sequence would be 2 over 3 pi, 2 over 5 pi, 3 over 7 pi, 2 over 9 pi, and 2 over 11 pi, etc. So that would have some sort of pattern as well. A lot of the sequences we're going to be dealing with will have patterns. It's possible some of them will not have a pattern, but they are still a sequence. It's just we don't know what the formula is. So these are all nth term formulas, so we can know, for instance, the 50th term of these sequences if we wanted to. Okay, so let's talk about limits and sequences. So the first thing we're going to look at is the limit of a function at infinity and a convergent sequence. We say the limit as x goes to infinity of f of x is equal to L. The epsilon delta definition of limit here would be for every epsilon greater than 0, there exists an m greater than 0, such that if x is past m greater than m, then the distance between the function and its limit is within epsilon. So what that looks like is, here's your function, f of x. And notice that it's flattening out, so the end behavior looks like it might have some sort of horizontal asymptote or something to describe the end behavior. So it does have a limit, we'll call it L. Okay, and then we have some epsilon, so we're going to draw epsilon 2. So here would be L plus epsilon and L minus epsilon. And somewhere once we get past m, the function will be within epsilon of the limit, which means it lives in that epsilon 2. So that m might be right about here, and then once you get past m, the function is going to be within the epsilon 2. Now let's contrast that with the limit as n goes to infinity of a sub n is equal to L, and that is defined as for every epsilon greater than 0, there exists a big natural number n such that once n is greater than or equal to n, this implies that the distance between a sub n and L is within epsilon. So the difference here is our function is defined on the positive integers and sometimes the non-negative integers, sometimes 0 is included. Okay, and etc. So there would be an example of a sequence there, and you notice that as we go further off to the right that the sequence seems to settle down, flatten out, and so that looks like it might have a limit. So we'll call it L. Then we have our L plus epsilon and our L minus epsilon. And so we want to find what's the n, or we just need an n such that past n the sequence is within epsilon of the limit. And so that big N might be right there based off of our picture there. And so once we're past big N, then our sequence is within epsilon. Okay. All right, so we're going to go ahead and do a little bit of examples of doing some proofs with sequences and showing their limits are, and I think in this case we're going to be looking at showing that the limits are 0. So I'm going to show the limit as n goes to infinity of 1 over n is equal to 0. So for the proof, we're going to let epsilon greater than 0 be given. And what we want is the function a sub n minus its limit with less than epsilon. So the distance between a sub n and L to be less than epsilon. So that's equivalent to 1 over n minus 0, and absolute value is less than epsilon. Well, 1 over n minus 0 is 1 over n, and the absolute value of 1 over n is just 1 over n because it's positive. Okay, so that'd be equivalent to 1 over n is less than epsilon. If we multiply by n over epsilon, which are both positive numbers, we have 1 over epsilon is less than n. And so this is what we need right here. Okay, so if we can get n to be larger than 1 over epsilon, then the rest of this stuff is equivalent, so we can get to our result. All right, so since the natural numbers are unbounded, that means there's no largest natural number. So since the natural numbers are unbounded, there exists a natural number, n, such that n is greater than or equal to, and let's go ahead and just say strictly greater than 1 over epsilon. It certainly could be greater than or equal to, but let's say strictly greater than 1 over epsilon. Okay, so if n is greater than or equal to big N, then because big N is greater than 1 over epsilon, by transitivity, 1 over n is all right, I had to fix a mistake there. So that means the reciprocal 1 over n is less than or equal to 1 over big N. And so this is using the idea, let's say that 10 is greater than or equal to 9. So how does 1 over 10 compare to 1 over 9? We reverse our inequality, and that's true as long as our values are positive. Now, 1 over n is going to be less than epsilon. Okay, so that's how we chose it, because we chose it as n greater than 1 over epsilon. So if we reverse our argument, we'll multiply this by epsilon over n, and so then we have epsilon is greater than 1 over n, which in turn is larger than 1 over little n. Okay, so now We have that less than epsilon. So 1 over n, which is equal to the absolute value of 1 over n minus 0, that's going to be less than or equal to 1 over n, which is less than epsilon. So we have shown that at some point in time, 1 over n is going to be smaller than epsilon. And this can be done with any epsilon we want. Epsilon could be 1 over 10 billion. We can find an n such that 1 over n is going to be smaller than, what did we say, 1 over 10 billion? Whatever that crazy number we came up with. Okay, so thus, this says that the limit as n goes to infinity of 1 over n is equal to 0. Okay, and that completes our proof. We'll go ahead and look at another example of doing an, it's not an epsilon delta proof, it's like an epsilon-N proof or epsilon-M proof. So here we're going to show the limit as n goes to infinity of 2 over 4n minus 3 pi is going to go to 0. So we're going to let epsilon greater than 0 be given. What we want is the not the function, but the sequence minus its limit to be within epsilon. So that's 2 over 4n minus 3 times pi minus the limit of 0. We want that to be less than epsilon. So 2 over 4n minus 3 times pi is less than epsilon. We're going to go ahead and multiply by the reciprocal here. Okay, so 4n minus 3 pi over 2, and then we'll also put an epsilon in the denominator. So this will become equivalent to, so all those values are positive, 1 over epsilon is less than 4n minus 3 pi over 2. If we multiply by 2 over pi, and again that's positive, so we have 2 over epsilon pi is less than 4n minus 3. So what we'll do is we'll add 3 and then divide by 4, which is the same thing as multiplying by a quarter. So you have 1 over 4 times the quantity 2 over epsilon times pi plus 3 is less than n. And that's what we want because the natural numbers are unbounded. We can find an n that's larger than this, and then we can reverse our argument and we have what we want. So again, we're going to say since the natural numbers are unbounded, there exists a natural number n such that 1 over 4, 2 over epsilon pi plus 3 is less than n. Okay, if n is greater than or equal to n, then 1/4 2 over epsilon pi plus 3 is less than n, which is less than or equal to n. And this is going to be equivalent to what we want. So 2 over 4n minus 3 pi is less than epsilon. Okay? And so that's enough to make our conclusion that the limit is 4n minus 3 pi. As n goes to infinity, that's going to go to 0. So what that proves is we're going to go to 0. So it doesn't matter where we're at. Let's say this is 0.002. Because we know the limit is 0, at some point in time, all the points are going to be in our sequence in here. Okay, infinitely many of them. Infinitely many of them. Okay. So in the next couple of examples, I've used Excel to plot what this looks like. So here I've done a plot in Excel of the sequence a sub n equals 2 over 4n minus 3 pi. Okay, and you can see that it is certainly flattening out to 0. Okay, and so certainly infinitely many points in the sequence are going to be very, very close to 0. Very, very close to 0. We're going to look at another sequence. This is going to be the sequence a sub n equals the sine of 1 divided by that sequence we just talked about. Okay, oops, went too far. So the a sub n equals 2 over 4n minus 3 pi. That's down here, that's going to 0. Now if we take the sine of the reciprocal of that sequence, notice that the output is constantly 1. It's always 1. And so we have infinitely many of the a sub n going to 0. Maybe we should call this b sub n just so we can distinguish them. So we'll call this one b sub n. So we're going to have infinitely many of the b sub n be at height 1. Now there's a function that you probably look at in Calculus 1 that has the infinite oscillation. I think we mentioned it earlier when we looked at arc length of something that does not have a rectifiable curve, which is a curve of finite length. And so this is the sine of 1 over x. And so what we have found with that sequence b sub n is it's going to keep outputting 1s, infinitely many 1s. And so that's going to show us that the limit doesn't exist, because we could also prove that there are infinitely many zeros as we get close to 0. Okay, so this was something looked at in Cal 1, the limit as x goes to 0 of the sine of 1 over x. We said that didn't exist, and our reason was probably an infinite oscillation. And we said that that was a non-removable discontinuity. Okay, so non-removable discontinuity. And so one way to show that this is discontinuous, maybe it's done in Cal 2, maybe it's done more in an upper division class, but you show you have two different sequences, one that goes to 1 and another that goes to 0. And so if you have two different subsequences going to different places, then so what I mean by that, I mean the limit of two different subsequences of a sequence, they go to different locations, then the limit of the sequence doesn't exist. And so this can be done sometimes in Cal 2, but I think probably more in upper division mathematics to show that this limit doesn't exist, and we say more than just an infinite oscillation. And the sequence a sub n equals 2 over 4n minus 3 pi. That is used to show that there are infinitely many points close to 0, and then the sign of those points is always going to be 1. Well, it's going to be the sign of the reciprocal. And so the sequence you would use for the infinitely many zeros would be, we call it c sub n equals 1 over n pi, and then d sub n would be the sign of the reciprocal of that sequence, which give you the sign of n pi. And where n is an integer, so we're talking about pi and 2 pi and 3 pi and 4 pi, etc. And the sign of all of those would be 0. And so that's how we would show there's infinitely many zeros as we approach 0, just as we have infinitely many 1s as we approach 0. So anyways, that is one of the applications of sequences, is we can use them in conjunction with functions. And so we'll see that a little bit later in the next video or two. Okay, so we'll see you next time.